Okay, let's unpack this.
Let's do it.
So imagine you're in your kitchen. Your goal, your high-level goal is to make a really good omelet.
Okay.
You're not thinking about, the precise physics of how a yolk separates from the white. You're thinking about the whole sequence.
Big picture.
But then you get to the stove and you seamlessly shift. You move down to that tiny, fine-grained action of cracking an egg just right so you don't get shell everywhere.
Right. And that ability to just shift your focus, that control over what we call decision granularity is so central to how we think, to adaptive intelligence.
And that's the problem we're talking about today, because current LLM-based agents, well, they can't do that.
They can't. Cognitive science suggests we don't really have a separate planning brain and an action brain. It's all integrated. But the models we build, they're not. They're structurally incapable of that fluidity.
They get stuck in these really rigid structures, and we see, I think, two main ways this whole thing fails them. First, you have the classic React agents. They just go back and forth. Reasoning, then a tiny action. Reasoning, action.
It's very step-by-step.
It's fine-grained, but it totally lacks any strategic foresight. It's like micromanaging cracking the egg without ever having the goal of omelet in mind.
That's a great way to put it. And then the second failure point is with agents that do have planners. They try to add that foresight.
But they separate them. You get this rigid wall between the high-level planner and the low-level executor.
And that boundary is just so brittle. The moment the environment changes, even a little bit, the plan is useless because it's totally disconnected from the action part. The agent can't adapt.
So that brings us to our mission for this deep dive. We're getting into ReCode. That's Recursive Code Generation. It's a new paradigm designed to smash that rigid boundary.
To achieve what the researchers call universal granularity control.
And the whole approach is unification, making planning and action fundamentally the same thing, just at different scales.
That core insight is so fascinating because it's so simple once you say it out loud. The boundary we've built between a plan and an action, it's artificial.
So how does ReCode see it?
ReCode's whole realization is that planning is just a higher level, more abstract kind of action. That's it.
So if they're on the same spectrum, how do you even define the difference between them?
Well, think about it like programming. A high-level plan is sort of like pseudocode. You're sketching out the steps abstractly, but you can't run them yet.
Okay, I see. And an action.
An executable primitive action is like the concrete code. It's implemented, it does something. They use the same language, but one is an idea and one is an instruction.
And ReCode's clever mechanism for this unification is to just represent everything as Python function calls.
Yep. It creates a common computational substrate. So primitive actions are just executable functions that can, touch the environment, like run, take spoon.
But the plans are different. They're these unimplemented, abstract placeholder functions.
Something like prepare breakfast. It's a subgoal, just waiting to be broken down.
And this is where the recursive part of ReCode comes in. The agent sees a placeholder, and instead of executing it, it has to decompose it.
Right. So let's walk through that process. It all starts with initialization. The task you give it, say, clean the kitchen, immediately gets converted into a root placeholder function.
Yeah.
Maybe solve, instruction, observation.
Okay, so the agent sees solve. And its first job is to figure out the next level of substeps. That's the expansion phase.
That's it. The policy expands solve into a new block of code. This block might have some primitive actions it can do right away, but mostly it's going to be new, finer-grained placeholder functions.
Like wash dishes.
Like wash dishes. And the executor just goes through this block line by line. It runs the primitive actions it finds.
But what happens when it hits wash dishes? How does it not just get stuck on this abstract idea?
It doesn't get stuck, because that placeholder triggers a recursive call. The executor sees the placeholder, and it calls the policy again, asking the LLM to generate a brand new code block, this time focused only on expanding that one subgoal.
Ah, I see. And this just keeps happening. It keeps breaking down placeholders until everything is a primitive action.
Until every single function call on the path resolves down to something executable.
And that is the crucial distinction. The plan isn't some separate document it writes at the beginning. The plan is the code, and it's generating itself on the fly as needed. That process is what dissolves the rigid boundary.
It means the agent's granularity is totally dynamic, it's context sensitive, it's a lot closer to that flexible intelligence we see in humans.
Okay, here's where it gets really interesting for me. The empirical advantages. If this structure is so much more natural, what does that do for performance?
The results are very strong. I mean, they tested ReCode across these really complex environments, ALF world, web shop, science world, and it just consistently outperformed the strong baselines.
Things like React or even those specialized planners like Ada Planner.
All of them. And when you look at the raw numbers, ReCode hit an average score of 60.8.
Which is a relative improvement of, what, 20.9% over the best baseline? That seems like a massive jump.
It is a massive jump. A 20% improvement in these benchmarks means it's much more robust. These tasks can take 20, 30 steps. So that jump means it's making correct, long-term strategic decisions way more often.
And this wasn't just a fluke with one super powerful model.
No, and that's important. The effect held true across different LLMs, GPT-4o Mini, Gemini 2.5 Flash, DeepSeek. It confirms the approach itself is what's powerful, not just the underlying model.
I saw they also looked into how deep this whole decomposition thing should go. I mean, if recursion is the answer, why not just go infinitely deep?
It's a great question. They did a recursion depth analysis, and they found this inverted U pattern. Performance clearly peaked at a depth of 8.
Okay, so too shallow is bad.
Too shallow, and you don't get enough hierarchical planning. The agent loses its strategic foresight.
But what happens if it's too deep?
Too deep, and you get what they call overfragmentation. If you're trying to plan every tiny sub-action 10 steps ahead, the sheer number of tokens and the complexity just causes performance to drop.
The system gets bogged down in details it doesn't need yet.
It does. So they found a hard limit of about 10 for the recursion depth was the practical sweet spot.
Now, beyond performance, there's the other huge factor, efficiency. I mean, cost is everything for real-world use.
And that's a huge win here, because ReCode generates these abstract, powerful function calls. Its overall reasoning path is much, much shorter than a reactive agent's.
Which means fewer API calls.
Dramatically fewer. A ReCode trajectory costs, on average, about 78.9% less than React and 84.4% less than Codact. Yeah, that's a staggering saving.
Wow. And the structural advantage also makes the model more efficient during training, right?
It does, because the agent is generating this beautiful hierarchical multi-granularity code as it runs. That code itself becomes a much richer training signal than, the flat action list from a React agent.
You learn more from each example.
You learn a lot more. And in their supervised fine-tuning experiments, ReCode hit better performance while using way fewer data pairs.
How much fewer are we talking?
It's a huge difference. On Science World, which is really complex, ReCode only needed about 3 of 500 expert trajectories to get high success rates. The React baseline needed over 12,000 to get similar results on tasks it had already seen.
So it's cheaper to run and cheaper to train.
Much cheaper and faster.
Okay, let's make this more concrete. The ALF World case study they use is perfect. The task is to find 2 alarm clocks and put them in a dresser.
Right. A multi-stage task. You have to search, move objects, and remember what you've done.
So how does ReCode start?
It starts by generating a high-level sort of hybrid plan. It's a code block that mixes abstract placeholders, like find and take, with simple primitive actions it can do right now, like run, go to dresser 1.
So it keeps the strategic goal in view. But then when the executor gets to that find and take placeholder, that's the trigger, right?
That's the on-demand decomposition. The LLM is called recursively, and it expands find and take into all the little detailed search primitives.
So it generates new specific code blocks.
Code like run the location ID, then run location ID, and finally run fitting obj ID from location ID.
And for a task like this, state management is critical. The agent can't forget where it's already looked, especially when it goes to find that second clock.
That's right. And after it places the first clock, the high-level plan has another placeholder called update allocation IDs. This forces the agent to explicitly manage its own state.
And when that function gets expanded...
It doesn't just refresh a list. It's smarter than that.
Yeah.
It intelligently slices the location list based on the last place it found something.
Yeah.
So if it found clock 1 at desk 1, it knows to start looking for clock 2 after that spot.
So it prevents redundant searching. It's essentially forcing the LLM to think hierarchically and save its state for later subtasks.
It makes it a really powerful tool for these complex sequential problems. The whole flow is this dynamic tree that expands from abstract strategy all the way down to fine-grained executable code.
So what does this all mean?
I think it means ReCode really does solve that core problem of fixed granularity by unifying the plan and the action into a single recursive representation.
It leads to these huge gains in performance, dramatic cost savings, and much faster, richer training.
It does. But, while ReCode provides the framework for this kind of thinking,
Hmm.
its success really critically depends on the base modder's own ability to generate that complex structured code.
It has to be able to stick to that recursive format.
If the model's intrinsic planning ability is weak, or it can't generate the code correctly, then the whole decision-making process is compromised from the start.
Which raises an interesting final thought for you, the listener, to mull over. If the power of next-gen AI planning is so tied up in its ability to write this very specific recursive Python code, does the future of adaptive intelligence depend more on a model's coding precision than, say, its narrative fluency?
Something to think about as these models start tackling more of the real world.